I was really excited when Richard asked me, gave me this opportunity to give a talk because of the history that I have with what used to be called the US-Japan Technology Management Center. But talking about AI systems and opportunities in Asia, I thought those are two concepts that are really interesting when they come together. You probably all know there's a ton of activity going on in AI in the world, and Asia and East Asia is a particular hotspot. So what I'll talk about today will leave you all experts, hopefully, in IoT technologies and innovation and how it's using AI technology and then what's going on in Asia and where I think there are opportunities. Now, the word opportunity is not only when you start a business yourself, but it's also when you can work with other businesses that are in Asia. So I'll talk about those two concepts. So let's get started. Today, what I'll talk about is from the semiconductor industry point of view. I work at Intel. As Richard introduced me, I'm a director of marketing in the IoT group. And so from the silicon perspective, there are various kinds of things going on in the evolution of AI. And I'll talk about what's going on at the network edge or at the edge. And don't worry, I know this is an academic institution, so I'll define what I mean by these terms. We'll talk about the background, I'll define the network edge, and we'll also look at the trends and market dynamics, and I'll talk about what's going on and how we're able to accelerate intelligent vision technologies with the partnerships and various kinds of business models that we have, including Asia. And then, of course, I'll leave you with some challenges that I think we have in the industry that we'll have to overcome. But first, I want to give a little bit of an introduction to how I got here. And it is kind of an interesting story, and there were a couple of revelations that I thought would be kind of entertaining. I started out, actually, before I even came to Stanford, in this program called the EAGLE program. When I was an undergraduate, just before my junior year, I found out that they were taking engineers and scientists, sending them out to Terre Haute, Indiana, where we have the Rose-Hulman Institute of Technology, training them in Japanese. I thought, wow, that sounds pretty interesting. Signed up, went there, learned Japanese, and that was the EAGLE program, Engineering Alliance for Global Education. I came to Stanford later on after going to work in Japan, and I took some courses from the US-Japan Technology Management Center. I actually put my transcript up here. And you'll see they had Japanese manufacturing, Japanese business culture, even an optoelectronics seminar, which were really cool. This is how I got to know Richard Dasher from these courses, also from working as a TA in his group. So I benefited more than once from working with the US-Japan Technology Management Center, which is the name of the US-Asia Technology Management Center back in the 1990s. And I got to work on a research project with a professor named Sam Wood in the Graduate School of Business. This was a very interesting project, not only because it paid my way through the master's program, but also because it was about how Sony was able to take some nascent technology and technology that was invented in the United States at a few different companies, the laser diode, and be able to mass manufacture them for consumer electronics, for CD players and DVD players. So it was a very interesting study of what Sony was doing with laser diodes. And what I later found out was all of that experience that I had in the EAGLE program and at the US-Japan Technology Management Center at Stanford was because the Congress, US Congress, had actually funded a program to train American universities to learn about Japanese technology management. And both of those programs were part of the list of the universities that were benefiting from that funding. So there were students all over the US at these universities in this program called the Japanese Technology Industry Management Program. I don't know the exact name, but the JIMT program. And it was really exciting to find out later on, wow, there was like a whole there was some meaning to what was going on with all of these programs, and I was very interested in learning about Asian technology management. So now we're going to zoom forward to 2018, and we know that artificial intelligence is a really hot topic. That's what's brought you here to this seminar. So here's some newspaper clippings, random clippings in South Korea, in China, in Japan, in India. Governments in East Asia and Southeast Asia are investing a lot of money and doing a lot that they can to be able to do what they can to introduce AI and take advantage of this technology. AI can do a lot, and it can do a lot for a lot of different companies. It's a super hot topic, as you can see, and it's booming. Now, there's a reason why it's booming, and we're going to kind of peel back the layers and see why it is it's booming from the semiconductor point of view. So first, I'm going to start taking you back to computer vision, and I'm going to talk about one of the biggest applications of AI, CV, or computer vision, and what we're doing at Intel to enable computer vision and AI in systems at the edge. So let's talk about computer vision first, and then we'll talk about what the edge is. So computer vision, you probably have heard of this kind of technology. You've probably taken pictures with cameras that can track people's faces and then focus correctly on them, or track your pets and then focus correctly on them. So this is technology that's been around for decades now, I believe. There was actually research in the 1950s and 1960s on being able to identify a face in a photograph, or to be able to identify the landscape versus the sky versus trees versus grass. And all of these kinds of fundamental classification problems or image tracking or detection problems, this was an area called computer vision, which has been around for over 40 or 50 years. So what has happened between 40 or 50 years ago and now? Well, back then, you were writing these algorithms by hand. You would write them presumably on punch cards and put them into the mainframe computers like the ones shown there. And then the mainframe computer would crunch out some data, and you'd be able to write these programs. They would run, albeit fairly slowly, and you would have these kind of ways to identify photographs. So now we zoom to the present, and we have AI and something called deep learning, which is a big area of AI, where you're actually training algorithms that are mimicking the human brain and the way the human brain operates, and you're training the algorithms to recognize something, or recognize faces, or recognize characters. And we also can run them in real time. We can also run them, because of AI and because of this deep learning technology, you can actually achieve very, very high accuracy. So now an algorithm can achieve 99 or 100, almost close to 100% accuracy with a very sophisticated AI algorithm, where in the past, maybe you'll get 70% accuracy. Maybe that was good enough. Or on your camera 15 years ago, tracking faces, maybe it didn't pick up everybody's face, but it picked up most people's faces. So that was good enough. But with deep learning, now with the larger your data set, the larger of the amount of data that you have to train your algorithm, the more accurate your algorithm can become. And also the more sophisticated the algorithm is. In other words, the more computations required by the algorithm, again, the more accurate it can become. And it's also now miniaturized. So you'll see a picture of a chip that looks like this, and we'll get back to what this chip does if you want to zoom in on the chip. Chips this small can now do much better than what those large computers could do in the 1960s. But it is still amazing that hundreds of millions of transistors on these chips can still do computer vision. So this can do roughly 4 trillion operations per second of 16-bit floating point calculations per second. And that can be used to do AI in a miniature product, like a small camera or a wearable or something like that. So let's move on to talk about what is the edge. This has now become a very hot topic, because now with the microelectronics getting smaller, lower power, and faster, you can actually make devices like some of the ones pictured here, whether in a retail store, you'll have some cameras, or cameras doing security, health and medical devices that are doing medical imaging. So I picked some example edge devices that are doing imaging. But in this area, you'll see they're devices that are at the edge of the network, because they're just terminated with some sensors, and they have a connection to the network, to the internet or the cloud in the back. So where the sensors are, that's called the edge. Those are edge devices. Now if you move back one level to where you would connect those cameras, let's say in this university you have some security cameras or some cameras that are connected to some on-site appliances or on-site network video recorders or gateways. It comes with various names, but this edge compute node is also considered the edge, because it's where these cameras are being terminated, and it may also have some intelligence. So you can have an appliance that also has to be fairly miniature, fairly low power. It's very different from the data center that you find, so where you're doing a Google search, online. It's actually data is going to a very large data center, very high power, very super high performance. But we're talking about little appliances that are going to be connecting maybe 40 cameras on this side of campus, maybe on the other side of campus you have another 40 cameras. They need to connect into these local on-premise appliances. So that's what we call the edge devices and the edge servers or the edge compute node. And then on the other hand, if I go to the other side of this continuum, you have the network hub that these are connected to when they're connected to the cloud. And then you have the cloud or the data center in the back. So you have this continuum of the cloud, which is where you have a lot of performance, maybe not so much regard to power, although you could argue we're trying to make these data centers green. So power is still a concern in the data center. But it's of extreme concern at the edge because you might have a wearable camera, or you might have security cameras that have to be very small and have to fit within a dome that can't. So the thermal issues, the cost issues, power issues, that's what we find at the edge. And that's why it's so exciting, is to be able to put the performance required for AI all the way into these edge devices and edge compute nodes. So that's what the edge is. So to give you an example of why the edge is so important. So here's, let's say, a device, kind of a small, simple diagram of a device at the edge. And then we have an edge compute node that it's connected to. And then that's connected to the cloud. So let's just say it's, in a hospital, you have cameras that are detecting where patients are moving around, or that, or in a factory where it's detecting whether people are wearing the right safety equipment. And then those cameras are connected to some edge server, and then the edge server is connected to the network. So the power required at the edge device is very, very low, maybe a couple of watts. Then the power, if you have to transmit the data to the edge server, maybe it'll take about 5 to 20 watts. And then if you have to move the data all the way and do some computation or image processing to detect things in the video in the server, then you're spending thousands of watts. So the more, to the extent that you're going into the cloud, you're actually spending quite a lot of power. That's an interesting concept. So you know what the edge is, and now you know how the edge is so important because of power concerns. So now let's talk about the opportunity for IoT in general, and then we'll start to talk about why Asia is so important. So there's a growing opportunity for AI, and from the silicon point of view, what we're going to look at in this chart is the total available market, or the number of billions of dollars available for silicon vendors like ourselves at Intel, and all the silicon vendors in doing what's called inference and what's called training. So to train a neural network, you actually want to have the power of a data center. You want to have as much compute capability so that you can get all of the images of faces you want into your face detection algorithm, and then you can create your face detection algorithm. But then there's also the deployment of the algorithm, or what's called inference, where you're actually running it on a little device or running it in a camera. And when you run it, then you want to be able to run at very low power, very high performance. So it ends up that over the next 5 years, what we're predicting from some of the analyst data that we have, that the amount of billions of dollars of silicon that's going to be shipped in the edge for deploying these neural networks is actually growing more than the data center, both inference, because you're talking, let's say you're talking to your little home appliance and it goes into the network and interprets what you're saying. That's in the data center, that's data center inference. Also data center training, the training technology that people are using. And both of those combined, it's still not growing as much as the endpoint. So the edge is actually very, very hot, and this is why a lot of companies are now trying to build very low power, very high performance devices for doing AI, because it's growing at a 25 to 35% annual growth rate over the next 5 years. So there's another dynamic to get you all up to speed with what's going on in the AI at the edge, which is that to the extent that the chip technology is doing more and more, the applications are now able to do more and are getting more accurate and more interesting, and there are more interesting use cases in all kinds of different areas. We'll go into that. But then in order to, then they're requiring more and then pushing back on the chip industry to be able to supply even higher performance at even low power, with even lower latency, with even lower cost. And so there's this virtuous cycle of the chip companies like my own developing better silicon that's enabling more interesting uses in various applications, and then it's just kind of circular. So there's a lot of exciting development going on, and almost a global race to see who can perform, the best algorithms that are the most accurate. And if you go to any of these academic conferences, for example, CVPR in the summer, or the NIPS conference in the fall, in December, a lot of academic papers coming out showing that my network is 1% better than the last guy's, and someone else who will then do 0.5% better than the last one. And so there's inching toward neural networks and deep learning algorithms in AI that can achieve more and more accuracy, and in some cases requiring less and less computation. So I've been talking about what are these use cases. So this is something also that applies anywhere in the world, but the interesting thing about some of these use cases are some of them are hotter in different regions of the world. So let's just take city, state, and federal. So federal, public safety, traffic congestion. There are different ways in which raising the IQ of the city means that you have cameras that can detect traffic congestion and other kinds of things, or delivering tickets to cars that are speeding through the stoplights. There's also, in finance and banking, having ATMs that can recognize what you'd like to do and be able to give you services better and more efficiently, making the customer experience even better. One interesting example in finance, going into a bank, and there's like 20,000 or 30,000, pick any bank, and they'll have a lot of different outlets all over the country. But they may only have mortgage experts, in certain parts. And so if the mortgage expert's not there, well, you have to call. But they'll have, maybe kiosks. You can approach the kiosk, get the mortgage expert, talk face to face, even if they're not on site with you. So that's one example of using technology in finance and banking, detecting your gender and wait time, and kind of using that data and doing some analytics if you're in line queuing up for a kiosk. Now, industrial and machine vision is a very big area. In countries like Japan, there are companies that do factory automation, robotics. Elsewhere in Asia, companies that are using technology to inspect a lot faster. If a human being is picking up a device and looking and trying to inspect, it could be a lot better if you've trained an algorithm to understand, based on millions and millions of images, what the defects are. So we'll talk about the industrial in a little bit more depth on the next slide. Also casino gaming, transportation, of course, cars are becoming automated, having autonomous vehicles, and also being able to detect not just outside the car for safety purposes, but inside the car. If you've left your cell phone behind, wouldn't it be great to be able to get notified immediately that you had left something behind in a taxi or something like that, or in an Uber? Home and retail surveillance, being able to have better cameras in the home, or even a thermostat that's smart so that when you're cooking in the kitchen, it'll know to adjust because it knows you're in the kitchen cooking. Or you're traveling to the living room and so you're away from the kitchen, so now it'll adjust. It's like having automatic home comfort improved through the use of visual analytics. That's another really key area for AI systems. And robotics and drones. So let's deep dive into two of those examples, and then I'll tell you a little bit more about what my company is doing and how we're using our relationships in Asia. But I just kind of wanted to give you a little bit of the background in this area. So let's look at a smart factory. So this is an example of, again, looking at the things at the edge, the devices at the edge, and also the compute node, and all the way into the cloud, what you might see in the factory of the future, whether it's a couple of years in the future or a number of years in the future. A warehouse that could be using robots to move equipment around. And of course, it uses vision to control the robots. You might also do sorting based on cameras that can detect and what items need to be placed where and how they need to be sorted. So there's a lot of computer vision and using these AI algorithms to be able to do very accurate kinds of warehouse sorting and various carrying of items. Also detection of safety gear. This was a demonstration that was performed by one of our partner companies, is detecting that you've worn the helmet, detecting that you've worn the safety gear. You can imagine you're avoiding accidents if you can tell which employees in the factory are not wearing the safety gear, and doing that kind of semi-autonomously on via cameras. And then of course, the data can be viewed maybe by PCs and other people in other areas. The data can go into the cloud and be controlled from there. So let's look at an actual real example. of how a factory is using Intel products. That's what we know. So if you look at these various different blocks, I'm going to start on the right at the edge where we have an industrial PC. So it's very typical in a factory that you want to have a very sturdy PC that's going to be running some kind of management of cameras. It'll also be have a very powerful CPU. So the cameras can have, in the case, in the picture here, we're showing Intel Movidius. The chip that I showed you before is the brand Intel Movidius. So this does 4 trillion operations per second of artificial intelligence on the camera input coming in. And then it's streaming that kind of metadata into the PC, and then it's streaming into an edge server. So the edge server then takes that data, and it can do higher level things. It can detect, okay, we found a problem on the manufacturing line over there, and we found a problem over there. And so it can kind of make higher level decisions based on the streamed metadata about where these cameras are, or what kind of product defects you're finding, or those things. Defect detection is actually the biggest reason why I think technology, AI technology is being used in factories. Because it'll save a lot of time, it makes the factory more efficient. And in fact, I've heard that installing robots in factories actually produces more jobs because it's more electronics to maintain, more robots to maintain. There might have been one person manually looking for defects before, but now you have a robot that can grab the items or from the manufacturing line, make sure all of them, all of the sides of the product are aimed at a camera, and then those images are rapidly being analyzed by AI algorithms to look for defects. Now the interesting thing then is then the data can be looked at using these dashboards, and you can review based across multiple factories through the dashboard what the status is and where you're finding product defects and such. So this is an actual use case. And one of the interesting things about why you need to do training of AI algorithms, even in these edge servers, is that you might find a new defect you didn't know before. And then you want to be able to transmit that information, update your AI algorithm to include that defect, have a new algorithm that's trained, and then spread that to the other factories if you have a number of them that are all building the same, similar products. So even at the edge, you sometimes have to do training of AI technology. So let's look at another example, smart stores. This is really exciting because you can imagine when you walk into a supermarket and you take something off the shelf, and it's the last one, it usually takes them some time to figure out that that was the last product. Inventory control, inventory management. It's very important to do this very accurately. It's sometimes upsetting to me when I go to a store to find something and there's nothing there, and then they go, oh, but we have one at that other site 20 miles away, and then you drive 20 miles, but they don't have it either. So this happened to you many times, I'm sure. But it won't happen when you have AI technology powering cameras that can actually be used to detect when items are pulled off the shelf or looking at inventory like actually on the shelf. And then using the metadata in the edge servers to look at the store analytics and inventory management. And there's also another interesting dynamic, is that when you're walking into the store and you pick something off the shelf and look at it and you realize it's a bit expensive and put it back, or you look at the label and look at the ingredients and then put it back. So that data can actually be accumulated, and then that manufacturer could be notified that of 100 people on average who are picking up their product, 50 people put it back on the shelf. So by tracking people throughout the store and tracking what items are being lifted by the person, those kinds of gestures can be recognized by behavioral analytics powered by these kinds of AI algorithms. And it's interesting also, I've met companies doing eye tracking, that in the store, the person's gaze and which products they're looking at on which shelves can also be tracked. And that's very valuable marketing information. So the supermarket of the future with this kind of analytics can hone in on which products are the most popular and put them and stock them up, and it'll probably make the consumer experience a lot better. And it also gives them a lot more quick ability to know the stores themselves, the ability to track their inventory. So that's another example of AI being used at the edge. But again, the technology needs to be super fast, it needs to be very miniature, it needs to be cost effective, it also needs to be very low power. So this is all a very big challenge for the industry. So now we're going to go into, shift into what is Intel doing in this area, and how are we finding opportunities in Asia, and how does this impact our business? So I mentioned before the Movidius silicon, which, here, show it once more. We're very proud of these processors that are very small, somewhat inexpensive, and can perform trillions of operations per second. So this is used to connect cameras and do the imaging of the camera. It can also do computer vision algorithms, various standard traditional algorithms, as well as the deep learning inference so that you can perform AI algorithms in these kinds of edge products. But it's not just a technical problem. So you'd think that, oh, if we build the right chips, and if we can make the chips high performance, low power, low latency, low cost, then shouldn't our business just grow and grow and grow? Well, it's also important that you have to scale the technology to get out to the developers who want the technology. And how do we scale to developers worldwide? That's where the opportunities in Asia really come in. And I'll explain in a little bit more detail. So one of the issues about the IoT business is that when we sell these chips, we're not selling it to the end customer. So let's say the end customer is a fast food chain, and they want to be able to put cameras into their store to be able to identify how fast customers are coming in, how fast they're ordering French fries, and they want to be able to serve those French fries fresh and not use as much oil and limit how much resources are going to waste by tracking people moving into their store. That's possibly a real use case. Will they buy these chips directly from Intel? Possibly not. Of course, they want to be able to call up an installer, just like you would install a home security system. The system integrator is then installing the equipment. Now, where does the system integrator get their equipment? They're buying the equipment from the appliance makers who are maybe building the appliances or building the cameras, building devices. And then those camera makers are actually buying the silicon from Intel. Or they're possibly even buying PCB boards that are made with the Intel chips. So you see there's a number of companies in the chain, and that's why there's a channel there's a whole big complex channel of customers and those customers and those customers before you get to the end customer. So it's a very sophisticated business. So what I'm showing up here now is how we make a business out of these chips in an industry where you have to sell to a device maker, the device maker or the appliance maker is then selling to a system integrator, and then they're getting to the end customers. The end customers may build the security system on a ship, or they might build the ship tracking system that's on the dock. But we don't talk directly to the end customer. Of course, we do talk to them and learn a lot from them, but we're selling through this channel. So one of the ways to sell through the channel is to work with partners on building boards. So we can build boards that have one chip, or even better than one is 2, and even better than 2 is 8. And so we have these kinds of hardware partners that are manufacturing these boards that are not manufactured by my company, but they're manufactured to be able to supply to the camera makers or supply to the appliance makers. So this is an example of one of those boards, and we've just launched this a few weeks ago. It's called the Vision Accelerator Designs, Intel Vision Accelerator Designs. And the exciting thing about it is that we've actually worked with a lot of these manufacturers that are in Asia that are experts at building boards. And these boards are not easy to build. You might think, oh, PCB board, breadboard, I've done that before. I've taken my graduate course in Stanford EE. I know how to do that. But when the chip is this sophisticated and it takes, and each of the pins on the chip are 0.4 millimeters apart, it's actually quite difficult to build one of these boards and to be able to solder them on. You can't solder them on by hand. So there's a lot of technology used in building the boards and also building them in a way that's very standard. So standard mini PCIe or standard M.2. So we rely on these partners to be able to build these boards, to be able to then get out into the industry. One example of a partner is KAGA Electronics. We announced earlier this year a relationship that Intel has with KAGA Electronics. This is their webpage. For those of you who speak Japanese, you can tell that they're talking about accelerator boards using deep learning, and that's what this is. So they have their own sales, they have their own distribution, they have their own business, and we are their quarterback behind them, shipping them the silicon, working with them on understanding how to build the silicon correctly from our reference designs, and then they can go off and do their own business. So if you're a big company in Japan and you're looking to build some kind of machine vision camera for industrial purposes or a factory automation camera, you can go contact KAGA Electronics and they can work with you on that. Another example partner based in Taiwan, I'll point out, is AAEON. AAEON's an interesting company. They do a lot of different kinds of boards. They do a lot of different kinds of form factor cards for different kinds of businesses. And they're out promoting the same kinds of products, and they make little dev kits. You can see you can plug this one directly into the internet to your Ethernet. So they're another interesting partner. And we have a number of other partners. Nexcom, who's been building robotics. So Nexcom builds robots that are connected to the PCs that have these edge server cards in them. Other companies like AdLink, IEI, and Advantech. So for Intel, the business can't really grow when we're trying to directly ship chips to customers directly, because then they can't use them. But when you have partners like these companies that are experts in building boards, experts in then customizing them for certain industries, some of them have their own focus areas like machine vision, robotics, retail, et cetera. So then it makes the business actually work. So in a field like IoT, where it is a channel business, you require partners like these, and they're really great to work with. And we also announced recently a larger partner program. So just those partners are on this slide, but you also have another a slew of different partners. Because some of these companies have to do software, and then they're plugged into the boxes that have these cards in them. Some of the companies are doing industry-specific application software or hardware and rely on those partners that are building the boards. And then we have other new partners that are coming to work with us. So we have a whole large ecosystem. And if you were to look at where all of these companies are, a large number of them are actually coming from Asia, from China, from Taiwan, from Korea, from Japan. There are many partners also in the US and Europe as well. We've also have so partners of different kinds, either in different segments. One example, Gorilla does video management software for security and surveillance. So we have a large partner program, and we're constantly working with these partners, and we have large partner teams that manage those partners. And part of the success of our IoT business at Intel is directly because we have this partner ecosystem. And we act like the quarterback because it's our silicon which powers what's going on, but it would never be successful without the partners, especially the ones in Asia. Now, there are some Tier 1 companies that we work with, and I wanted to bring out one example, Alibaba. Now, who has not heard of Alibaba? It's a large company that they're transforming the way people are doing computing. And Intel has also announced publicly that back in September, just 1 month ago, that we're working with them on some basic platforms for edge computing. So it's not just us taking our silicon and shipping it out for whatever the customers want to do. We're actually creating something called the Joint Edge Computing Platform. So it's really exciting, and we plan to showcase that at the Tokyo Olympics in 2020. So there are Tier 1 companies that we'll work with very closely, some of them in China, like Alibaba, and other parts of Asia. So I think one thing I was going to say in the very beginning, when I lived in Japan over years ago, I realized there's a way of thinking, something cultural. There's a very methodical way of thinking. And I keep thinking that people are very methodical in Asia. And I think one of the reasons which many of our ecosystem partners are so successful in areas of high tech that are on the bleeding edge, like AI systems at the network edge, is because of the way of thinking, being very methodical, coming up with systems that actually work, trying and trying again. And I think in other parts of the world, we also have many, many people and a lot of innovation. So I'm not pointing out that Asia is somehow peculiar or different than the rest of the world. But there's a methodical way of thinking that I think goes hand in hand with the culture that I think is the fuel toward, in some of these kinds of partnerships. Fuel in some of these areas. So I'd like to leave you with some ideas about the challenges that we have in the semiconductor field. I think many different semiconductor companies are going to find these kinds of challenges that we have to overcome to make more of these edge devices and edge products possible. So if you look at, so I created this little graph. It wouldn't pass maybe an academic test, but in general, what we're seeing today is neural networks, like this neural network called ResNet 50. And if you send images one at a time, which what we say is batch size equals 1. So one at a time, you're sending an image. It makes up a video stream through this neural network, and you're trying to do some detection or some classification. How many inferences it can do per second. So how fast this neural network can perform on a given platform, what we're finding today is maybe 20, 30, 40, 50 frames per second. So you can run the video at 50 frames per second, and for every frame it will capture and detect what you want it to detect, or however you train the neural network on whatever training data set that you have. So that we're down here in terms of performance. But every year over the next 5 years, I see it's going to grow exponentially. So to 100 frames per second, to 1,000 frames per second, and we're going to require maybe 3 orders of magnitude more performance at the same power of 5 to 10 watts moving down the road. So every year what we've seen is now people are running more sophisticated neural networks, or they're running multiple sophisticated neural networks. I mean, imagine in a device you want to detect something and then you want to classify it. You detect the object and then you want to classify. Is it a dog or a cat? So that's 2 neural networks you have to run, and the speed and everything else factored in. I think there's a really rapid climb in terms of the required performance that you need, yet can we spend more power on it? No, because it's going to be in a miniature edge product, or it's going to be in some kind of product where the thermal design is such that it has to be very miniature. So what are the kinds of steps that we're taking in the semiconductor area to try to combat this kind of issue of the requirements in new kinds of use cases? And let me just say, I see a trend in Asia where there are very interesting use cases in retail or in industrial manufacturing. And I would even say that in China, I think there's a very aggressive breakneck speed at which companies are trying to implement these in actual factories or in actual retail environments. So this may even be a conservative look at what the semiconductor industry has to do to be able to support those applications. But anyway, some of the techniques that we're doing are we're taking neural networks that have to perform at like 16-bit resolution, and we're having to compress them down to compute them at 8-bit resolution or 4-bit resolution or 1-bit resolution. And as you require fewer bits, you can do more computations, but then it's also not quite as accurate. So you lose some accuracy, but you have to do very special techniques to try to counterbalance that. So that's one technique. Also taking these neural networks where some of the neurons and some of the data coming through might be zeros, in which case you might be multiplying 0 times 0. Why would you ever do that? So you can take advantage of the fact that some of these multiplications you're doing are sparse, and so you can do various techniques to take advantage and get even more computation capability. Or you have efficient memory. So that's something that we've been working on a lot at Intel, is how to get data in and out of the chips and how to get the data flow to require less power and be much more efficient. Many of you may not know this, but the processing of the data versus the movement of the data, in many cases the movement takes up much more power than the processing itself. So don't be fooled by companies that say, well, our processor is capable of this much at this power. Well, but what about moving the data in and out of the chip? If it's inefficient, then that could cause a lot of power. So that's another area. Also, companies are coming up. You'll read articles about new startups that are coming up with accelerators and different kinds of engines for neural networks, neural computing. Our chip has something called a neural compute engine that puts into hardware capability that can do it very, very efficiently, but it's not programmable. So then there's a trade-off between programmability and hardwired functions. And then also compilers and tools. So there's a lot of things that the technology companies like Intel have to do. But then we take advantage of working with companies that are very innovative, and also working with companies in Asia that help us fan out in terms of our partnerships, and then we can be successful. So to conclude the talk, before we have some questions and answers, I'll just say the future is kind of unknown, but a lot of companies are doing really interesting things, and it helps a lot to be closely watching what's going on in East Asia, Southeast Asia. Countries like China, Japan, Taiwan, Korea are working very, very hard in AI systems, and I'm really proud that companies like Intel are there to help support their work, as well as in the rest of the world. But with the partnerships, I think there's a lot of really interesting things that you'll see coming from our company. So That's it for today. Thank you very much.